Now it's time for our next lecture. Our speaker is Badr Ouali, and his topic is predicting smart meters consumptions using in-dB machine learning. Hello, Badr. Before you begin, I would just like to say a few words about this lecture. So basically, data science, as you all know, has the potential to help businesses solve many use cases and gain the competitive edge, but the relative difficulty of putting machine learning models into production is a big impediment to the use of this to the use of this in enterprise. In this session, we will share with you how you can use the Python interface of Vertica to perform the entire machine learning cycle from data preparation to model deployment. Badr works as a data scientist for Vertica worldwide, and he enjoys sharing knowledge and insights related to data analytics with colleagues and peers, and he has a sweet spot for Python. So, Badr, again, thank you for coming. How are you?
Thank you, Stefan, for inviting me. Yeah, I'm doing very well. Very glad to participate to this event and to showcase a little bit Vertica. How are you, Stefan?
Excellent. We don't have a lot of time, so I don't want to take up any more of yours. Good luck. Just go to your presentation. Excellent. Here it is.
Okay, perfect. So let's go. So what I will do before switching to the notebook, I will just do like a quick introduction of VerticaPy and Vertica in database data science, because it's very important to be aware that nowadays we are all working in this, a lot of people are working in this amazing field, but we are encountering a lot of problems when we speak about data deployment. When we speak about huge volume of data, we are facing a lot of trouble. Yes, indeed. Just look, there is a lot of comparison between sampling and the full data set, but what I would say is quite simple. Just imagine doing anomaly detection on a sample of data, whereas anomalies are just outliers of a distribution. We are losing a lot by downsampling. Sometimes we find a solution, sometimes we find a way of exploring our data by sampling in some kind of correct way. But we are losing a lot. So why not using the entire data set when doing the study? Because we are limited with in-memory softwares. And that's where Vertica brings you a huge advantage, because Vertica is a database made for analytics. And we developed at the top of Vertica many machine learning models in order to scale, in order to parallelize the process. These new models are not built using third-party tools. They are built from scratch in C++ in order to be fast and scalable. And in Vertica, you can follow the entire data science cycle, both in SQL and Python. We will see, of course, the Python interface, but you must understand that you have all these built-in functions that will totally help you to solve like a lot of business use cases with few lines of code, from data preparation to model deployment. And you have a bunch of functions also to ingest your data in order to, for example, explore your data. So typically we will see a lot of these functionalities right there. Vertica has its own model management system, so which means that you can work with model the same way you're working with tables and views, and we will see it directly with the Python interface. And Vertica is typically not just a simple data warehouse, because you can do much more than this, because nowadays we see like a lot of databases and we say, okay, which one should I choose? They look like the same. No, here there are all the analytical part that Vertica can cover. And if we don't have, for example, a specific function, it is possible to code it with 4 programming languages in order to increase the possibilities. And multiple ways of solving all these data science challenges are available in Vertica. And we will focus on the Python front end, which is the perfect combination between Vertica, MPP, columnar database, and Python, which is totally flexible. And we all know Python. Very easy. I have a method. I can call the method. I can get my attributes with just few lines of code. And I just have to think about like a method, and it's surely exist in Python. The idea here is to combine this scalability that Python doesn't have with this flexibility offers by Python with all these objects, these easy methods, which means we created new objects which will expose scikit-pandas-like functionalities. So you're playing like almost the same way. You're playing with pandas scikit-learn, but this time with a new generation object. And this object will push all the heavy computation to Vertica, which will compute all the aggregation and help you by offering you all this scalability. But in the other hand, we have Python, and Python has a lot of modules that can help you to develop graphics, that help you to explore easily your data, to do data visualization. So why not using, for example, Matplotlib to draw graphics, and why not, for example, following the entire data science cycle directly by embedding a lot of functionalities. Just to summarize this API before going through the example, you have access to new generation object that will push back all the heavy computation to Vertica, which will allow you a lot of advantages. You take advantages of Jupyter and Python, so very easy, right? .core, I get my correlation matrix. .describe, I get my statistics, but you get the advantages, of course, of the MPP scalable infrastructure, which is Vertica. And by the way, no data movement, you're winning time for data movement. And you're using this object that will push, of course, this computation using a connection, which means you can collaborate with user. When you create a model, another user can use it. There is this collaboration that is created, and you have all the possibility of seeing graphics, which means that you have the entire data science cycle in this API. Example. You import the data frame, you can create it, and you can describe. So what's going on on the client side? It will send a SQL query, and you can see that here it's a specific built-in query of Vertica, which means that with summarizing columns like sending, select, average, standard deviation, variance, etc. But it's in one function that is parallelized in order to be fast and scalable instead of using multiple aggregation, which can be very, very expensive from a query perspective. Vertica parallelize the result, and you get the output. So now let's go through the example, and let's go through the smart meter notebook that I created right there. So we will play with this type of object like the virtual data frame. Again, it's this object. It will keep in mind the user modification in order to send queries to Vertica. Vertica compute all the aggregation, send back the result, and then we can display. For example, here is just select a number of rows by displaying my virtual data frame. Right there, we have a classical example for smart meters. When we deal with smart meters, we have a bunch of information. Most of the time, we have, for example, many sensors, and we get, for example, the energy consumptions, and we can get some over information depending on how we define the business use case. Because we all know that in data science, the most important part is defining the business use case. Because I can have many study in mind, but at the end, I need to solve something. I need to bring some value to my business. So I need to understand what I want to do. Here, it's clear. I have some data about smart meters consumption in Ireland. And my purpose will be just, for example, to predict the consumption depending on the type, the residence type. For example, if it is an apartment, if it is a house, in order to say, okay, let's say I will predict it in order to see if what is normal, what is not normal. Like this, I can adjust the energy consumption in some region. What type of data do we have? Of course, the smart meter ID. So we have a unique identifier in order to know the type of smart meters, and we will see it in the over data set. Daytime, very classical of time series. Time series data are just data set containing like this daytime value and the value of the smart meter. So we have this numeric value, the energy consumption by the smart meters during this specific time. We have also information, but this information are more global. That's why I like this example. How can we merge different data sources? We just have in an entire Ireland, we can be more precise if we get longitude and latitude for the temperature and humidity. But unfortunately, we don't have it. We have just the temperature, humidity, and the daytime. And we will consider that in Ireland, we have approximately the same temperature and humidity, which is totally not true. But for sake of simplicity, just imagine that we didn't get the exact longitude and latitude. And you will see that during this data science journey, we are finding so much difficulty to gather the data. It's very, very complicated to get a correct data source, data quality, sorry. So here, and we have information about the smart meters. For example, here we have meter ID, the residence type, I think 1 apartment, 2 house. So the different type of residence, we should look at how it is encoded. And we get the latitude and longitude, but of the smart meters, not the weather. So this one, very easy. I will be able to use it in order to create some regions. So you will see how I will do it. But first, before I will just scroll up a bit just to show you how it is organized. When we deal with time series, what we want regular interval of time. I want, for example, each 1 hour, the energy consumption, for example, or each 30 minutes. But I really want to get a regular interval of time, because otherwise, what's going on? I cannot use my ARIMA model. I cannot use my VAR model because they expect regular interval of time. So slicing is a huge problem in time series. But just imagine slicing terabyte of data, like gigabyte of data, terabyte of data, like a huge, let's say a huge volume of data. Then becomes a problem because slicing is very expensive. And that's why we implemented this different slicing method directly in Vertica. So here I can slice in a regular interval. And what I will also do, I will, when I slice, I have regular interval of time. So I can then join the daytime, which is also in regular interval of time, each hours. Like this, I can create this new data set, which is the combination between the two of them. Because at the end, the over table is very easy to join because we can join it directly with the smart meter ID. But you see, I succeeded to join the humidity and temperature, even if we will see it, but during this study, it's not very, they are not very important variable. But what I want to show you is how it is easy, for example, to slice. You can see it each hour, the daytime. I'm using interpolation, gap filling, linear interpolation in order to fill my gap each hours. And I have the approximate value of the interpolation for each smart meter. And I get the humidity and temperature. So then what I can do, I can save my result as a table because we know that, for example, joining different elements specifically in daytime can be very, very expensive. So after you can do all the operation and then just create a view, which will not be expensive. But for the sake of simplicity, in order to work in a very fast way, what I'm doing, I'm just saving the result as a table using my virtual data frame. You can compute aggregation quite easily. For example, right there, we can see that we have 1,000 different smart meters, 3 different residence type, and longitude and latitude around Ireland. What I want to do with the longitude and the latitude, I want to build some clusters in order to have a simple model. Why? Because what we want in data science is to generalize. We like to have categories with a lot of elements. In order to find these elements, what I need to do is, of course, draw, for example, this kind of curve, the elbow curve, which will help me to determine a suitable number of clusters when I'm reaching a certain point. Here, when we look at the scatter plot of the some of the residents, we can see that we have some of them here, 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 here. We can say, okay, it's approximately 6 clusters. But what if I don't have like this visual graphic in order to determine this number of clusters? I'm using this type of elements, the elbow curve. The elbow curve, which I would compute the error of my k-means around different number of clusters to identify what is suitable. And here it is. We can see that like 6 could be suitable, even 4 could be suitable according to perhaps one cluster there, one cluster. But by looking, we can say, okay, 6 could be a good solution. But this method can be very efficient when dealing with many clusters. I got a use case with base station, and typically in this use case, I had to determine a suitable number of clusters, and it was more than 1,000. And you cannot look at the eye and say, okay, 1,000 is a good number. No, I need to group this region in order to do my study. So now I can import my k-mean model, like the same way I'm importing it in scikit-learn. So verticapy.learn.cluster. I can create my model. Do not forget, in Vertica, the models are stored. When you create a model, it's stored in database. It's automatically deployed where the data resides, inside the database. So that's why I'm giving a name to my model, because you can deal this way with model versioning and deal with the different model name, look at the attributes, etc. I will create the k-means with 6 clusters and use my longitude and latitude and see what will happen. I will add my prediction in my virtual data frame. As you can see right there, I'm adding it. So as region, so now we have a different region. And then I can draw a scatter plot. Depending on the situation, the scatter plot can be slightly different, but here it worked. Here you can see my 6 clusters, and I will use these clusters in order to feed my model to see, okay, if a region in a region, some people have high energy consumption compared to the other. It can be like a good predictor, but we will see that with energy consumption, it's almost stable. It's a use case that is almost stable. You can expect some kind, like approximately the same energy consumption. But do not forget that this year, because of the epidemic, because of the coronavirus, many people stayed at home. Was it expected? No, it wasn't. So we need typically to find how we can predict this energy consumption in order to, for example, know the action we can take in case too many residents have too much high energy consumption at the same time, to avoid this kind of event. What I will do, I will join using my smart meter table in order to get some other information on the residence type. As you can see, we have the region, the residence type, and other values. And our data set is clean, so we can typically save like a table of the result. It will generate some SQL in order to save this table. And then what I can do, of course, I can look at some of the missing values, and we can see that I have some missing values right there for value. And I have some missing part, not a lot of missing values. So I will not bother by knowing if this missing value is missing at random, not missing at random, in order to find a strategy. Right there, what I will do, I will just drop them because they are too few. And then what I can do, I can group by, for example, for the study, let's say, now my dataset is clean. I can solve many business use cases, predict the energy consumption in a specific region, predict in the entire Ireland, predict predicting the resonance type according to the energy consumption. There are plenty of use cases. What I will do, I will just try to predict the average consumption per region to see what's happening. So I will group by my element per region, residence type, and date. And you can see that you can write direct SQL code also in our group by statement. And I can, as we are speaking about energy consumption, what we want to predict is the cumulative, the cum sum of the energy consumption. So I can create the feature I want to predict right there using the cum sum function. You can see how easy it is. I can group by the elements. I can order by whatever I want. Very, very easy. Whereas for a lot of API, you will have to order it yourself with sort and then try to compute the cum sum. There are many API that allows you the cum sum, but here, just remember that you have a function rolling that will allow you to do moving windows of a lot of different features, standard deviation, percentile count, etc., to compute amazing features. So I have my cumulative value. What I can do, I can draw the cumulative value per region, and then I will just show you what I really want to do. So here I will draw this graphic of a cumulative sum using the different region, like some kind of area plot, in order to showcase you the linearity of the process. But as we are dealing with like, let's say, a consequent volume of data in order to draw the graphics, that's why it can take like 20 seconds, perhaps more, in order to draw the graphics. Because here, when we deal with line plots, scatter plots, we are loading some points in memory, and that's what we want to avoid. That's why it's always preferable to take the part of time you want to show, because there is no aggregation possible with a line plot or a scatter plot. And we can see the linearity of a process for each region right there. So what I will do, I can get the dummies. I can encode the different region. If I want to use, for example, a linear regression or any other models, here very easy, because we can clearly see the trend. It's a cumulative sum, by the way, but we can clearly see the trend, so it will be very easy to do a prediction of this energy consumption as expected on the beginning of the study. So what I will do, I'm saving as a table, and then I can compute, for example, a correlation vector of my target, and I can see that it's very correlated to the time, to the elapsed time. Of course, we are dealing with energy consumption. Energy consumption has a trend, and when you get a trend, of course, what's happening, you are correlated with the elapsed time, which makes sense. What we're gonna do now, let's do some machine learning. I will use a cross-validation of my linear regression right there. I will use, or as I'm dealing with a Hessian matrix, I will use a BFGS solver, and I can look at my different folds. I have 99% of R squared, very good model. I could have used a more complex model than the linear regression. Could you have used, for example, an autoregressive or an ARIMA model, but it's not needed for when you see like a clear trend like on this study. But typically, what you must understand is always, like in data science, what we like to do is to discover the data, to try to find the relationship between the data. And at the end, when we create this model, we totally understood what we want to do, because if we don't understand the business use case, we are locked. As I explained before, we have thousands of use cases for the same data set. And what we want is, okay, let's say I want to solve this. Can I do it? Do I have like a good data quality or integrity? What should I do in order to get more accurate result? I have to answer to all these questions because, like in a project, to tell you, data science project can take 1 month, like it can take 3 years. It really depends on what we want to do. And of course, we can win a lot of time when the data is in the database and we are bringing the analytics instead of exporting, sharing CSV file, where we are losing a lot of time by bringing the data out and trying to find a solution to bring the algorithm in. When we are ready, I can just fit, of course, my model, look at the features importance. As expected, the elapsed time is the most important feature, but we have much more there are much more methods in order to explore the model, in order to understand it, and to find relevant patterns. Here, just to conclude on this study, what we did, we have a data in Vertica. Vertica is an analytical database. You can ingest the data directly in Vertica using any ETL you want. Like this, the data, for example, let's imagine you have your smart meters. Your smart meters have this type of sensors. These sensors can send data to devices, and then you can use an ETL in order to prepare as you want this data in order to ingest it in your database. So here, there is all this process that can be managed on the backside. Then there is the analytical part. So here it is. I'm using like this API in order to play with my data the same way I'm playing with in-memory tools, but I'm not moving my data. My data is in Vertica. I'm playing in Vertica inside the database, which means that I don't have to waste time in order to deploy my model, in order to deploy my data preparation. Everything is happening directly where it should be. And that's what we did in order to predict the smart meter conceptions.